What you'll see in a lot of structural design books and sometimes analysis books is a curve that looks something like this. What we're trying to illustrate here is that the load effects, the maximum moment or shear or axial force in the member is not one number. Even though we'll calculate it like that, the reality is that there's some natural variation. Perhaps it's described by this bell curve type shape. Uh, we'll call those the demands. We want, of course, the capacity to be larger than demand. And the same thing is true about capacity, that somehow we, even though we'll calculate one number, the truth is that there's natural variation and there's also uncertainty in the models that we're using, that we don't really know the capacity to one specific kind of number. And you say, well, can't you test it and then you'll know it? Well, yeah, but then it's failed, right? Well, then you'll create a model. Yeah, exactly. But that model's not exact. But maybe it's better and there's less variation here than you see on the demand side. And that's why this curve for the capacity is narrowed, right? And it's a little bit higher because the area under these curves would represent total probability, which would be 100%. So I haven't quite gotten these two drawn maybe perfectly to scale because again, the areas should be each at 100%. The vertical axis here is the probability density, just like mass density, but now probability density. You integrate that under this curve and you get the probability value. So if I want, what's the likelihood that the demand is less than this particular value, then I just find that area. On the other hand, what I really tend to do is I say, what's the likelihood that the demand is higher than that? And what's the likelihood that the capacity is less than that? And that combination of things turns out to be what we call a convolution integral, to then try to figure out what the likelihood of failure is. Capacity low, demand high. And that's what we're really after here in structural design, is to try to adjust this capacity curve to a place where we have an acceptably small probability of failure. So let's see how we might calculate that for a specific situation. Right? Let's say that the capacity is drawn from a normal distribution that has a mean of 100, has a standard deviation of 30, and that the demand is also of a normal distribution with a mean of 80 and a standard deviation of 40, right? And we'll look at the form that is the safety margin. So M equals C minus D. So when C is larger than D, that's a good thing. When it's less than D, that's not a good thing. And we want to have some sort of acceptable positive margin there. And we would, 100 minus 80, that's 20, that's a positive number. But wait a minute, there's these variations going on here. So here's how this plays out, is that we've got some sort of model for the distribution of both the demand and the capacity. And when they're both normal and they are independent of each other, then we get that M, the safety margin, is also going to be normally distributed. The mean, because we have a linear combination here, the mean of the margin is just equal to the mean of the capacity minus the mean of the demand. It's the same kind of math that you learned back a long, long time ago. 100 minus 80 is 20, and that's your average safety margin. But when you get to the variance, that's no longer your straight arithmetic. It is probability math, right? And it's basically that combined variance, in this case for linear combinations, is going to be the same as the hypotenuse of a right triangle, where each one of these is the side of the triangle. So that variance is equal to 30 squared plus 40 squared, and then you get 50 squared, take the square root of that, and you get the standard deviation. So now we'll have the key parameters that we need to describe the distribution for the safety margin from a probability standpoint. So let's go find out what the likelihood of failure is. That would be when the safety margin is less than 0, right? And then because it's a normal distribution, we'll standardize that. We'll subtract off the mean and divide the whole thing by the standard deviation, right? That's going to be this thing called the Z, or standard variant. And then you've got then the number side of this, 0 minus the 20, that was our mean, divided by the 50. And that then gives you a value of minus 0.4. So you look up in the tables, or you use your normal distribution calculator, and the probability that Z is less than minus 0.4 is 34.4%. Oh, now wait a minute. That's actually a huge failure likelihood, right? When we're looking at structural design, let's just say it's an agricultural building. Well, for a yielding kind of failure limit where we have warning of impending doom, we're looking at 1.25 times 10 to the minus fourth per year as our estimate or target failure likelihood. That's a 1 in 8,000 chance here, right? And that's not what we got here. This is like a 1 in 3 chance. So there's a ratio of about 2,666. This is that much more likely to fail than what our target is for even the less riskiest or the least risk type of facility under the least dangerous type of failure that we might have. So this is an enormous failure likelihood. And how do you change it? Well, one, you start figuring out how to increase the capacity by shifting this out to the right. That was the controlling influence here, is really these two things there. There's not a lot we can do about the variance of the demand. There is some that we can do with the variance of the capacity, but even then there's some limited control, but we can shift that over and we can get that further apart. Now, the problem with all of this kind of a model and that kind of way of calculating things is we don't always have normal distributions involved here. That was just a nice way to illustrate how this goes. And if we look at this in terms of the safety factor instead of, or utilization ratio instead of the safety margin, even with this and do the same calculation, we'll get a different number as a result. And that shouldn't be, right? I mean, the likelihood of failure should just be what it is. We're just trying to estimate it. And the problem is we need a approach that is invariant to the form. And the way you do that, it turns out, is a natural log type of approach. And then you got to do some other things to deal with the distributions that are not what you see here. But this will at least illustrate the basic idea of how we go about trying to set up the probabilistic basis for our design codes.